In the last video, we saw a brief introduction to the field of quantum computation and quantum information. We also talked about quantum bits or qubits and saw the block sphere representing. Now let's move further. So we all know a single bit classical logic gate, that is the NOT gate, given as this symbol, which has a single input and a single output. The operation of this gate is simple, that is to invert the input bit. For 0, the output will be 1, and for 1, the output will be 0. But how to realize this simple operation for a single qubit? Since it is a linear state, that is psi equal to alpha 0 plus beta 1, and inverting this input implies we'll have beta 0 and alpha 1. This operation can be realized using a quantum NOT gate, which is represented in a matrix form given by x, which is equal to 0 1 1 0. To operate this gate, we'll represent our state psi as this column matrix, where the top entry corresponds to the amplitude for 0 state and the bottom entry corresponds to the amplitude of 1 state. So now to see the operation of quantum NOT gate, we have x times alpha beta will give you beta alpha, that is the inputs are inverted. How this works? We know our x matrix, that is for our quantum NOT gate, is 0 1 1 0, and when this operates on alpha beta, we'll have beta alpha. You can try it by yourself. So from this equation we can see that our quantum NOT gate has inverted the input qubits. Now we know that a quantum gate on a single qubit can be described by a 2 cross 2 matrix. But what are the constraints on this matrices? Can any matrix represent a quantum gate? One of the condition is that these matrices must be unitary. That is, for a matrix U, U dagger U must be equal to I. This is the condition for a unitary matrix. So for our quantum NOT gate, which is represented by this X matrix, X dagger X must be equal to I. Another thing is that the output qubit state must also be normalized like the input state. That is, this psi state was normalized. So the output state psi dash must also be normalized. Now let's see a few examples of a single qubit quantum gates. First one is the Z gate, which is given by Z equal to 100 minus 1. For a state alpha 0 plus beta 1, when operated by the Z gate, we'll have output as alpha 0 minus beta 1. So it has flipped the sign of the one state. The second example is the Hadamard gate, which is given by h equal to 1 by root 2 1 1 1 minus 1. The operation of this gate on 0 state gives us 0 plus 1 by root 2, which is halfway between the 0 and 1 state. Similarly, the operation of the Hadamard gate on 1 state gives us 0 minus 1 divided by root 2, which is also considered as halfway between 0 and 1. So in a nutshell, for a state alpha 0 plus beta 1, when an Hadamard gate is operated on it, we'll have the output as alpha 0 plus 1 by root 2 plus beta 0 minus 1 by root 2. If you'll see, this gate might look like a square root of NOT gate, but conversely, h square is not a NOT gate. That is, h square is equal to I, which implies that if you apply the edge gate twice on a state, it will give you the original state, or you can say that it won't have any changing effect on the state. So this is the visual representation of the operation of the Hadamard gate on the block sphere. So for the state psi, which is equal to 0 plus 1 divided by root 2, firstly this operation rotates the y-axis by 90 degree, followed by the rotation of x-axis by 180 degree. Now let's talk about multiple qubit states. For a classical 2 bits, we have 4 possible states, that is 0 0 0 1 1 0 and 1 1. Similarly, a 2-qubit system has 4 computational basis states that is given by 0, 0, 0, 1, 1, 0 and 1, 1. A pair of qubit can exist in superposition of these 4 states given by the state vector psi equal to alpha 0, 0, 0 state plus alpha 0, 1, 0, 1 state plus alpha 1, 0, 1, 0 state plus alpha 1, 1, 1, 1 state. And the normalization condition implies that alpha 0, 0 square plus alpha 0, 1 square plus alpha 1, 0 square and alpha 1, 1 square must be equal to 1. Now let's talk about renormalization for a while. Suppose for a 2-qubit system, initially we measure a subset of a qubit, let's say the first bit, which gave us 0 with probability alpha 0, 0 square plus alpha 0, 1 square. Now we obviously know that 1, 0 and 1, 1 states are redundant. So the post measurement state should be renormalized. That is multiplying the state by a constant to ensure that the sum of all probabilities is 1. So we'll have a new post measurement state, that is psi dash, which is multiplied by a normalizing constant n, and the state after the measurement looks like alpha 0, 0 plus alpha 0, 1, 0, 1. Now the condition for the normalization is that n alpha 0, 0 square plus n alpha 0, 1 square must be equal to 1, which implies n square alpha 0, 0 square plus alpha 0, 1 square equal to 1, which will give eventually n as 1 divided by root under alpha 0, 0 square plus alpha 0, 1 square. So putting the value of n in our new post measurement state, which is now renormalized, we have psi dash equal to alpha 0, 0, 0, 0 plus alpha 0, 1, 0, 1 divided by root under alpha 0, 0 square plus alpha 0, 1 square. This is an important case for renormalization of post measurement. Now let's see quantum gates for multiple qubits. We have classical multiple bit gates like AND, OR, XOR, NAND and NOR gates, out of which NAND and NOR gates are considered as universal gate. That is, any function on bits can be computed from the composition of these gates alone. The prototypical multiple qubit quantum logic gate is the control NOT gate or C NOT gate. It is given by a UCN unitary matrix. So it has two input qubits given as these two lines. The top line corresponds to the control bit and the bottom line corresponds to the target bit. The operation of this gate is given as if the control bit is 0, the target bit is left alone. That is, for 0, 0 state, the output would be 0, 0. That is, the control bit was 0, so the target bit was left alone. Another similar state will be 0, 1, which would be 0, 1. For a 0 control bit, the target bit is same. But if the control qubit is 1, target qubit is flipped. That is, for 1, 0, the output would be 1, 1. For the control qubit 1, the target qubit is flipped from 0 to 1. Another example is 1, 1. For the control qubit 1, the target qubit will be flipped to 0. So in a sense, it is a generalization of classical XOR gate. That is, target qubit acts like the output of XOR gate. So to understand this statement, we can see that for the input qubits, which can be represented as the input of our XOR gate, the output of our XOR gate is similar to the output of our target qubit. One more question arises is that can other classical gates be realized as unitary gates similarly like quantum NOT gate represents NOT gate for classical bit? The answer is no, because it is not possible. There are two reasons for that. First is irreversibility and second is not invertible. To discuss the first, reason, let's take an example of XOR gate or a NAND gate. So, for an XOR gate or a NAND gate, for a given output, we cannot know the input. That is, for one, we have two inputs. So, there is a loss of information. So, these classical gates are irreversible. For the second case of non-invertibility, we know that all quantum gates are unitary and all unitary operators are invertible. Another thing about universality is given by the statement that any multiple qubit logic gate may be composed from C naught and the single qubit gates that we saw earlier, which is a classical analogous to our NAND and NOR gate acting as a universal gate. Let's see the last topic of this video. Let us try to realize a quantum circuit. The given simple quantum circuit contains three quantum C0 gates. Each line in the circuit represents a wire in the quantum circuit. This circuit has a simple task of swapping the states of the two qubits. That is, AB will become BA. So in order to see how it's done, we'll take the case where A is equal to 1 and B is equal to 0. In order to realize the swapping, we are not taking similar values of A and B. So for the first operation, that is for the first C naught gate operation which we saw earlier, AB will be A modulo B. This addition modulo is commutative. That is, A plus B will be equal to B modulo A. Now, for the second operation, we have a inverted C naught gate. So, our state A comma A modulo B will become by the operation of the C naught gate, which is this state will remain same since it is in inverse fashion. This state will remain same and this state will have a addition modulo along with this state, which can be given as A modulo A plus B comma A plus B. Now to simplify this operation, we have A equal to 1 and B equal to 0, and this addition modulo is simply the operation of XOR gate. So let's see what A modulo B will give us. A modulo A plus B is nothing but 1 modulo 1 plus 0. Now 1 modulo 0 is 1 and 1 modulo 1 is 0. So we are getting 0, which is equal to B. This whole operation will eventually give us B. So the final state will be B comma A modulo B. Now for the third operation, we have B comma A plus B, and again it will be operated by a C naught gate, which would be this state will remain same, but this state would be moduled by this state. So it would be B comma A plus B modulo B. Again, to realize this state, you can do the same operation and eventually you will get A. So we finally come to the state where we have B and A. So this simple quantum circuit, which comprises of 3 C naught gate, has finally achieved the operation of swapping. That is, AB has become BA. I hope you understand this operation. So in order to study these topics in much more detail, you can refer to this book of Quantum Computation and Quantum Information by Nielsen and Schwang.